All right, thermochemistry and stoichiometry. Remember, enthalpy is how much energy is given off or absorbed into a system. Enthalpy measures a change in how much heat flows. Again, a negative delta H is exothermic, a positive means it's endothermic. In a chemical equation, stoichiometric ratios between the moles of substances determine the enthalpy of the reaction, or how much energy is given off. And the key point, stoichiometry is used to determine how much energy is flowing based on how much reactant is being used. Okay? So here's an enthalpy problem with stoichiometry. When 1 mole of methane is burned at constant pressure, 890 kilojoules of energy is released as heat. Calculate delta H for the process in which 5.8 grams sample of methane is burned at constant pressure. Okay, so first thing we need to do is write a balanced equation for the combustion reaction, where we have this. Okay, we know that delta H is negative 890 kilojoules because it's released, and therefore it's negative. So therefore, here's our thermochemical equation, where I have this. 1 mole of methane will produce, combusted will produce negative 890 kilojoules of energy, or 890 kilojoules of energy will be released. Okay, so what do we have? We have 5.8 grams of methane. We know that 1 mole of methane is equal to 16.05 grams. Do the ratio of 1 mole of methane burned releases 890 kilojoules. We also want the delta H for 5.8 grams. Well, since we only have 5.8 grams, we don't have a whole mole of this. If we had a whole mole, it would be an easy conversion, where we'd get 890 kilojoules. But since we have less than a mole, we want to know how many kilojoules of energy are going to be released. So therefore, we set it up always in 2 steps. First, we figure out the grams to moles of whatever substances we're dealing with, and then we figure out moles to delta H. Okay? So, we figure this out. Here's my conversion to moles, and then here's my second step to convert to delta H. Now this 1 can be substituted depending on what the coefficient of whatever we're talking about comes into play. So when we do this, we get negative 320 kilojoules of energy. Therefore, it's being released. So take a look at this reaction. Reaction occurs in heat packs used to treat sports injuries. Here's our equation. We have iron plus oxygen makes iron 3 oxide, and we get 1,652 kilojoules released. So we know it's exothermic. So how much heat is released when 1 gram of iron is reacted with excess O2? Well, take a look here. Here is my mole conversion. Here is my energy conversion. And notice the 4. The 4 came from the balanced equation from the previous problem. Okay, where I had a 4 right here. Okay, because it takes 4 moles of iron to make that much energy. Okay? So therefore, it takes 7.39 kilojoules of energy is released, which is the same as this. Another sample problem, hydrazine N2H4 is used as rocket fuel. When 1 gram of hydrazine is burned, how much heat is given off? Well, always you're going to have to need a balanced equation, and also how much energy is produced from this whole process. And notice how if 1 mole of hydrazine is used, I get 618 kilojoules of energy. But since I'm not dealing with 1 mole of hydrazine, I'm only dealing with 1 gram of hydrazine, how much energy will be given off? So we set it up this way, again, 1 mole, and we get 19.3 kilojoules released. Here's one more final problem, again, where you take gaseous butane, is burned in cigarette lighters. Again, notice how if we have 10 grams of this, how much energy will be used. The 2 moles comes from this, and we get that as our answer. Okay, so this is our mole conversion, this is our energy conversion, and so on and so forth.